Hi. In one of the last videos I showed you how bit patterns can be used to represent unsigned integers. In this video I want to show you how we can build a device in Circuitverse for adding such unsigned integers. In order to do that, I will first show you on the iPad a mathematical idea that we then realize in Circuitverse. You will see that the algorithm that I implement in Circuitverse for adding binary numerals is basically the same that you already know from adding decimal numerals. And first of all, I want to begin with an example just to analyze this then a bit more general so that we can see that it actually can be just transferred in the same fashion to binary. So adding this decimal numerals with 1, 2, 3, 4 and 5, 6, 7, 8. We do in the following way. We would begin here in this column where the digits have the smallest weight, the least significant digits, and then we have 4 plus 8. We have to add 2 digits and the result would be 12. Then I need 2 digits for the result, and 1 digit goes here and the other one goes here. Then in this second column, where I have to do the next computation, I have to add 3 digits. 3 plus 7 gives 10, plus 1 gives 11. So here goes the 1. Here I have a carry of 1. Then I have to add these 3 numbers. 2 plus 6, that's 8, plus 1, that's 9. So in this case I just need 1 digit, but I also could say the carry in this case is 0. Then you see in general we have to add 3 digits after the first computation. And then we have here 1 plus 5, that's 6, plus 0, that's still 6. And then we have here 6, and we have a carry of 0. That means we have here no 5th digit actually. So let's remove that so that you not think this is some octal representation. Now in the next example I want to add 2 4-digit decimal numeral, but in this case the result should require 5 digits. And that should be the case if I add 8, 7, 6, 5 with 4, 3, 2, 1. We start here in this column, 5 plus 1, that's 6. So I just need 1 digit. The carry is therefore 0. Then I have here 3 digits, 6 plus 2, that's 8, plus 0, that's still 8. And we have here again a carry of 0. Then here we have 7 plus 3, that's 10, plus 0, that's still 10. So we have here a 0 and here a 1. And then we have here 8 plus 4, that's 12, plus 1, that's 13. So we have here a 3, carry of 1. And then we actually have here a 5th digit in the result. And if we now are dealing with a fixed amount of digits that are allowed or used for representing the operands and the result, it means we somehow will just see this result, and because we actually would require this 5th digit, we would have an overflow. And that means that we cannot represent the result with the available number of digits. So this here indicates an overflow. Now I want to look at this example a bit more general, and that means for an arbitrary base b, and want to convince you that many things are just still the same. For example, that you only have carries of either 0 or 1. You never can have a carry of 2 or more, no matter what base you are using. So let's write down this computation just a bit more general. So the first number has digits A3, A2, A1, A0, and we add this with a numeral where the digits are called B3, B2, B1, B0. And then in red, the computations that we do. We have to add first 2 digits only, A0 plus B0. This would then result in S0 and in general carry C1. Then we have to add these 3 digits. This would give us a S1, C2, then we have here a S2, C3, S3, and then a carry C4, and in general an S4. So the first thing that we can observe is in the last computation we will add 0 plus 0 plus C4. So that means from that we see that S4 always equals C4. Now let's also look a bit more into the details how we would compute, for example, this S0 and this C1, and how we can describe this mathematically for a general base, in this case upper B, so that we don't mix it up with the digits of this operands. So A0 and B0 are values from 0 to uppercase B minus 1. And that means A0 plus B0 is a value from 0 to 2 uppercase B minus 2. And for computing S0, that's actually the remainder after dividing this sum by uppercase B. So we can say S0 is A0 plus B0 mod uppercase B. So of course this here is a value from 0 to uppercase B minus 1. This carry is what you get when you compute A0 plus B0 divided by uppercase B, and by doing an integer division where you truncate the result, or you could say if you round it downwards to 0. And this here only can be a value either 0 or 1. That's because this sum here never can be 2b or more, so we never can get something like 2 point something. And so we already see that this first carry never can be 2. Now for computing S2 and C2 we can do the similar thinking. A1 plus B1 plus C1 is some value in the range from 0 to 2b to uppercase B minus 1. And then of course S1 also would just be the remainder after adding this digits here and dividing it by uppercase B. And C1, the second carry, would be what you get after dividing this sum by uppercase B and then truncate the result. Now this value also here never can be larger than 2 uppercase B minus 1, because that's the maximal value that we can have here. Yeah, so also here we just can have a value of either 0 or 1. And so this will be in general also the case for C3 and C4. So that means we can say overflow is indicated if and only if this last carry is 1. Yeah? And now we can think about what kind of subproblems do we need to solve in order to do a 4-bit adder. Well, we first of all have to know how to add 2 bits, and then in general, and that will be the second step, how to add 3 bits, because we will use the base 2. So for adding 2 bits, and the right term for that would be for building a so-called half adder. We have 2 inputs. We have a Boolean function which is vector valued and has 2 inputs. And the inputs I will call A and B. And the outputs will be called S and C. And then we just write down here all possible cases and what result we expect. 0 plus 0 gives 0. So we would have here a sum of 0 and a carry of 0. And 0 plus 1 gives 1, so we would have here a sum, or what we write in the result as the sum of a certain column as 1 and the carry of 0. And also here 1 and 0. And in this case we would have here a result in the column, a sum of 0 and a carry of 1. And that's what we would do if the base is 2. Now this here can be easily be realized with logic gates, because if you look at this column, then you basically see this is a exclusive OR for A and B. So we can say this is an A exclusive OR B. And what you see here in this column, this is an AND of A and B. And before we continue to think about how to build a full adder, let's go to Circuitverse and realize this half adder here. Now let me first call this project for bit adder and save it online. Now I have to actually add a description. I will do this later or probably never. And let's also close this tab here and zoom in. So for this half adder, I need two inputs, A and B. So let's give them already labels A and B. Then I need two outputs, S and C. And then I compute S with an XOR and the C with an AND gate. And this will be connected with A and this will be connected with B. And then we realize this Boolean function. Now for building this full adder, we want to use this half adder as a building block. And in Circuitverse, you actually can reuse a logic circuit for another logic circuit. What you have to do is in this property box, you call this, for example, half adder. Some would call it HA, but that's more expressive name, half adder. And then you can click here on this edit layout, and then you will see in later steps we can use this kind of as a black box for building this full adder. But first we have to think about what this full adder is actually supposed to realize. It has to add 3 bits, and we have to think about how to make use of this half adder. So let's go back to the iPad. For building a full adder, in order to add 3 bits, we exactly could approach this problem as before by building up a table, which in this case would have 3 inputs, A, B, and C, and 2 outputs. But then we already have to begin to think about renaming things, because usually we would like now to call these outputs S and C as before. We also want to compute 2 bits. So we have a C here, here, and here. So we have a name conflict. Now, the meaning of this C is actually that it's the carry bit that we got from the previous computation. So I want to call this C in. And this is the same C, so it's also called C in. And this C is actually the carry bit that we want to compute, so it will be used for the next operation probably. So now we would start to fill this table on the input side with all the possible bit patterns, maybe like that, and so on. And then fill out here the output side with the expected results. So for example, here we would expect 0, 0, here we would expect 1, 0, 1, 0, and so on. And this approach certainly would work as it did before. But I already mentioned that it's possible to use half adders, 2 half adders, in order to create this full adder. And from this approach, it's possible, but not so easy to see how to use these half adders. And to show you a more mathematical way to directly go to this nice solution, how to combine these half adders, I want to go back to the half adder and first of all describe it a bit more formal. So this is a Boolean function, let's call it h, and it's vector valued, it's mapping from b squared to b squared. Now if I have h of ab, this is vector valued with a component that I can call h1 of ab and h2 of ab. But like here in this table, I can also call the outputs just briefly s and c. And the property of this function, let's also write that down here, is defined such that a plus b equals 2 times c plus s, 2 times the carry bit plus s. Now, first of all, convince yourself that this formula is equivalent to this table. We can describe Boolean functions with formulas or tables, both is possible. And now we can think about how to make use of this half adder. I mean, obviously we want to compute a plus b plus c in, maybe in a way that we first add a and b using a half adder and then use a second half adder to complete this computation. And now I can write down this idea in a formal way. A plus b is 2 times the carry bit that we get from the first half adder. That means h2 of ab plus the sum computed by the half adder, h1 of ab. And to that we want to add c in. Now in order to make this a bit more easy to write down, I will rename things. This carry bit here will get the name c tilde, and this sum that we computed the name s tilde. And then I can rewrite this as 2 times c tilde plus s tilde plus cn and use parentheses like that. Then I have here the sum of 2 bits, so I can use again half adder. And I first have this 2 times c tilde from before plus, and then here again 2 times the carry bit computed by this half adder, which gets s tilde and cn as input, plus the sum computed by this half adder. Then again I can give this names. I will call this here c tilde, and this here actually gets the name s, because I'm claiming this is the s that we actually want to compute. Now let's rewrite this again. This is the same as 2 times c tilde plus c tilde tilde plus s. So again we have this form where we have here a single bit and here a bit multiplied with 2. And now I just have to show you that the sum of c tilde and c tilde tilde never can be 2 or more, and that I actually can call it c and that it's actually just a bit. Recall that we showed for the more general case where we have an arbitrary base that the carry that we compute in one column never can be more than 1. We only can have a carry of 0 or 1. So it cannot be possible that we have a carry here and a carry here. One of them has to be 0. And that means we have actually here something which has a value of either 0 or 1. So calling this c makes sense, and if this property holds, then we exactly have what we want. We have a sum and a carry. Now let's write down how we actually now compute with the two half adders, the s and the c. For s it's simply this here, and then we have to plug in the meaning of s tilde. So we have h1 of s tilde and cn, which is the same as h1 of h1 ab in the first component and cn in the second component. And then we just have to think about how to do the wiring in circuitviz. But basically it's just reading the formula and realizing this with click and point. So then C is the sum of these 2 bits, and actually it's the same as an OR, because not both of them can be 1. So we can say this here is the same as C tilde or C tilde tilde. Recall this here is the same as this here, just because we know that not both bits can be 1. Maybe you also want to write that down somewhere explicitly. So now let's plug in this. C tilde was defined here. So we have here just a carry bit from the first half adder that we used. And then this OR gate or OR operation together with H2 of S tilde, that's H2 of H1 AB and Cn. And that means this here is what we now have to realize or implement in circuitviz. Now, before I begin with the full adder, let's go back to this edit layout button, and then I want to make this a bit more slick, thinner, so that I can really use it as a convenient building block, so that I have some nice logic circuits. Here I can decrease the height. So that's how I want to use it for the next circuit. And I go here to new circuit, and this will be called full adder. And now I need 3 inputs, A, B and C in. And 1 output, 2 outputs, as before, S and C out. And here the labels A, B and C in. Okay, and now I can choose here from this circuit to insert a sub-circuit, and here I want to insert the half adder, and actually I need it twice. I think I can copy and paste it. Now I have it twice, and then I just have to do the math in circuitviz. So first I want to compute with a half adder the sum and the carry bit for A plus B. And then I have to compute the sum of C in and what we got from the first half adder, which was called S tilde before. And this should give us here the sum that we want. And then I can use an OR gate for building the sum of this C tilde here and the C tilde here. And we can use this OR gate for building the sum, because not both of these carry bits can be 1. And then we can check out 1 plus 1 plus 1 should be 1 carry 1. And if we just have 2 bit set, we have a sum of 0 carry 1, and now we can validate what we did. Now, once we have this full adder, we actually can do what we initially wanted, to build a 4-bit adder. And for that, I built just another 4-bit adder. And in the previous video, I also showed you how you can have input with more than 1 bit, and here we want to have a 4-bit input field for A and or B. So let's also label it A and B, and I want to have a 4-bit output. Actually, I can put it here, increase the bit width to 4, and then the orientation of this wire that we get from the input has 4 bits. We have 4 wires and we split it to 1, 1, 1. So now I can pick up the single bits from A, and the same I need for B. So maybe I rearrange this a bit. Okay. And now I could use a half adder for summing up here this least significant bits. But actually you will see in some later videos why it's actually a good idea to even use for this operation where we're actually just adding 2 bits to use a full adder. And just for now I will not mention it. It's just, let's say, easier to plug in 4 times the same thing, which is actually not true. So for some reason I just want to use only full adders. So for the first bit, maybe here, second column, third column, and fourth column. And now it just takes device here called a constant value, and this is what we just use here to connect this C in, so it will always be 0. Now this A is the bit that we get from here. Now this B is the bit that we get from here. And then we have a sum, the first bit. Let me also copy this here. I can already compute one of this output bit, or it's already computed, because that's what we have here. Now this carry bit that we get from the first full adder becomes the C in for the next one. And what we also compute here, and maybe I have to carefully connect this thing so that I don't mess up things. So that comes from here. And I think you see the trick. You somehow have to think ahead how to do the wiring. So maybe I just stop here, prepare this wiring a bit more careful, and show you the result. It's not a beauty, but it's doing its job. So now the wiring is actually working. Now you can check out that it's actually doing what it's supposed to do. Try out a few different examples, but of course the next nice thing would be to use hex displays to actually make it more visible what we are actually computing. What is also left is that, for example, in this computation where I have in A all bits set, and I have here a bit pattern of 0, that's where we have a overflow. This 5th bit is missing. What is left is to pick up this last carry bit, which is indicating this overflow. So let's also use an extra output for that. Maybe I also change the orientation so that I can now do the wiring without too many problems. Now I can connect this to here, and then you see in this case we have an overflow. If I would set this bit to 0, we don't have an overflow, and actually that's what we need in general. The operands as an input field, the output, and also this extra bit for indicating an overflow. Now, in order to connect some hex displays to it to make it more nice to use, I want to create a next circuit, demo circuit, where I will use this 4-bit adder as a building block. Now if I select here in the insert circuit the 4-bit adder, you will see the following problem, that some outputs don't have a name. And the reason for that is that I haven't used a name label here. And maybe you encounter this problem sooner or later as well. So the name for this 4-bit output field will be S for sum, and this here I will just call Cout, because this is the Cout that might be useful if you want to build up an 8-bit adder, which might be an interesting assignment. Okay, so now you see it already changed the layout of this building block. Also, let's zoom in a bit, and I can use again input fields, but now I can focus more on the usage of this adder. So this goes to A, this goes to B, and then I just connect the hex display to S, and I also want to hex displays to see what I'm actually computing. So this first hex display shows the value or the bit pattern of A, and this is the bit pattern of B. Or maybe I will do it even nicer. I put here in between a bit of space, and then I also show you how you can do labeling in circuitverse. And that's here in this menu, and then I will use one label plus, make this a little bit bigger and put it here, and we have a nice demo circuit. And another one will be used for an equal sign. And you see here 3 plus 7 is hex A, and 7 plus 7 is hex E. And of course you also see that, for example, here hex F plus, for example, 1, or if you interpret it as an unsigned integer, 15 plus 1 would give us a 0, so you also need this bit for indicating some overflow. In this case, you see the result is actually not representable. You also can, by the way, use some LED. And then you also see from the LED alert. That's it for this video. Now you can think about how you can use two 4-bit adders in order to build an 8-bit adder. Bye.